the distortion was getting from bad to worse. So it's just a visualization, just for you to get a feel as to, when you have a nonlinear load, what it can actually do to the current waveform. So let me move to the more important part of the presentation. So here, trying to look at some very common day-to-day applications, and it is an interesting find from a document that I found from the United States, that some of the very common day-to-day applications, like the ceiling fan at home, our common refrigerator, the fridge at home, the microwave oven, a vacuum cleaner, a fluorescent ceiling lamp, television, desktop computer, and printer. They have got very, very poor power factors, as you can see, particularly desktop computer and printer, television, and we don't realize it because we use these equipments daily so much, but we do not realize that that they are actually not very, very good when it comes to identifying the power factor, and they all relate to current. So this is just an extract from a document that I found related to power quality issues that talks about total harmonic distortion. I'm going to come to total harmonic distortion a little bit later on this presentation. So the data which is in the blue box that gives the total harmonic distortion typically for each of those practical common day-to-day applications, and then it gives the true power factor. So we are going to talk about displacement power factor and true power factor. The true power factor, because of all of these loads, majority of them being nonlinear, you'll see that the true power factor is very, very low. Very basic first principles, probably, first year, second year of electrical engineering, you'd have all studied a voltage sinusoidal curve and a current curve. And this is typically for a linear load. So with the linear load, the relationship between voltage and current waveform are sinusoidal, and the waveforms are pretty much proportional. So the current waveform is pretty much proportional to the voltage waveform. And typical examples of linear loads are transformers, motors, and capacitors. So there is obviously, depending upon whether it is a lagging load or a leading load, the voltage and current waveforms will be somewhat different, but they will be proportional in the sense that they will represent the same nature as such. So this is what a linear load actually means. And the typical linear load would be a transformer or an electric motor or even capacitors or even inductors. This is the nonlinear load. What is in a nonlinear load? What happens is that the current is not proportional to the voltage, and it fluctuates based on the alternating load impedance. Examples, there are plenty of examples of nonlinear loads in today's world. Basically any power electronic, any electronic device is a nonlinear load. So examples could be rectifiers, variable speed drives, computers, printers, TVs, servers, telecom systems, switch mode power supplies, SMPS as they're known as. And what happens is in nonlinear loads, they draw currents in short pulses. And these pulses, they distort the current waveforms, which in turn then generates harmonics, which can then lead to power problems affecting both the distribution system equipment and the loads connected to it. So the blue the blue curve is the voltage waveform, and if the load is a nonlinear waveform, then the distorted current looks like what is shown in red. And majority of the harmonics, or most of the harmonics in practice or in the practical field that we see, is because of nonlinear loads. And that's why I wanted to start off by showing the fundamental difference between what a linear load and a nonlinear load is. Again, talking on first principles, this is a typical harmonic spectrum. Some of you may have seen, some of you'll be seeing it if you work in the practical field in power factor correction, in harmonic analysis. You will be looking into a harmonic spectrum. So what is a harmonic spectrum? A harmonic spectrum consists of a fundamental, which is the 50 hertz component, and then you've got the third harmonic, which is the 150 hertz, the fifth harmonic, which is the 250 hertz, and so on and so forth. So you've got the fundamental, the third, fifth, seventh, and there could be even higher order harmonics. That red curve that I have drawn is an arbitrary curve just to show that where it actually ends above the fundamental. So that's basically the overall root mean square of the RMS value. So this could be a harmonic current spectrum, or it could be even a harmonic voltage spectrum. So the root mean square of the RMS value of the current will be an RMS value comprising of the fundamental component, the third harmonic, the fifth harmonic, seventh harmonic, and all the other odd harmonics. A little bit more around the first principles. So each harmonic on its own, which is a third harmonic or the fifth harmonic or the seventh harmonic or the fundamental, individually they are all sine waves, but they are all sine waves with different frequencies. So the fundamental is a sine wave with 50 hertz. The third harmonic is also a sine wave with 150 hertz. The fifth harmonic is with 250 hertz, and seventh harmonic is with 350 hertz, and so on. You may be seeing that there is no mention of even harmonics here, and that is basically and fundamentally because even harmonics only appear when there is no half-wave symmetry in the periodical wave. And in a power system, though we may have distortions in current or voltage waveforms, but the waveform is mostly symmetrical. And what we mean by symmetrical is that the negative half cycle of the mirror is exactly the mirror image of the positive half cycle. So maybe as a small task for all of you who are listening here, and if you happen to be a student, you can draw a curve for yourself representing the fundamental, which is 50 hertz. Draw for yourself what would a 100 hertz curve look like? What would a 200 hertz curve look like? And you'll find an answer yourself why the even harmonics, which is the 100 hertz, the second harmonic, the fourth harmonic, which is the 200 hertz, do not actually come in the equation because they offset each other. Moving on to the relations and between power factor and harmonic distortion. So voltage and current harmonics are fundamentally produced due to nonlinear loads, and these increase power losses and therefore have a significantly negative impact on the electric utility distribution systems and components. While harmonics and power factor have a very complex relation, and losses that arise have a very complex relationship, but one way to measure harmonics is by understanding the power factor of that complete nonlinear system. So by understanding the power factor, it gives us a good idea about what is the level of harmonic distortion. And it is useful when comparing the relative impacts of nonlinear loads, providing that obviously harmonics are incorporated into the power factor definition. So power factor and harmonic distortion, they are intertwined. And one way to understand the level of harmonic distortion is by looking at the power factor figure. And when we are looking at the power factor figure, we do not look at the conventional displacement power factor because the displacement power factor is probably more applicable to linear loads. We are looking at more nonlinear loads because in today's world, we talk of mostly nonlinear loads. And when we're talking of nonlinear loads, it is really the true power factor which is important, and that is what includes the effect of the harmonic distortion. So just a couple of, again, basic theory, and as I said that I didn't want to, load you with too much of formula and theory. That's not the objective of this webinar session. So again, a very simple linear load, and you've got a power supply, you've got a resistive, we've got a resistor, and then we've got a typical linear load, which can be an induction motor. We've got the voltage and the current relationship, and in this case the true power factor is also the displacement power factor, which is basically the cosine of the phase angle difference. So it's pretty straightforward, nothing more complex. This, I think all of you would have come across this number of times, even from your high school days. Now we move into to look at how power factor becomes a little bit different when it is under non-sinusoidal conditions or in a non-linear load. So considering non-sinusoidal situations where network voltages and currents can also contain harmonics. Some harmonics can be and are caused by system nonlinearities such as transformer saturation, but most of the harmonics, as I previously said, are produced by power electronic loads such as adjustable speed drives and diode bridge rectifiers, switch mode power supplies for basically power electronic devices. And the significant harmonics amongst these are usually the odd harmonics, namely the third, fifth, seventh multiples of the 50, 60 hertz, so that these are the frequencies of interest to us are typically in the low audible range frequencies. A couple of basic relationships of voltage and current, looking into from more complex non-sinusoidal relationships. So I'll probably skip this slide and go to the next one where we introduce the concept of total harmonic distortion current, total harmonic distortion V. So the subscript I and the subscript V denotes current for I and V for voltage. So what's total harmonic distortion? So total harmonic distortion mathematically is basically, it is actually pretty simple. It says that it is the ratio expressed in percentage of the total RMS value of all the harmonics to the fundamental RMS. So I1 is the fundamental component. So basically it talks in a sense, what is the composition of the harmonics? So the sum of the third, the fifth, the seventh, the ninth, all the way to the highest order harmonic, that divided by the magnitude of the fundamental current, which is the 50 hertz current, and that ratio expressed in percentage is the total harmonic distortion. Similarly, it is for voltage as well. Now, I've skipped, there's a big algorithm formula, you can run into a couple of pages to actually come to this final formula. I've skipped all of that, but just coming straight to the relationship in a nonlinear load condition, true power factor, as I've said that it is true power factor, which is probably more important, is more or less the same as the displacement power factor, but the relationship is quite complex. As you see that in a linear load, it is basically a cosine of the phase angle difference. Here it is 1 divided by square root of 1 plus total harmonic distortion divided by 100 square. So basically that total harmonic distortion is typically expressed in percentage. So you would come across in the real life people talking about, application engineers talking about total harmonic distortion 5%, 10%, 20%. So if you have a nonlinear load or a nonlinear load system where it could be different types of load, and if you have, say, a total harmonic distortion of 5%, you put 5% in THDI and use this formula, you can do the calculations yourself, but I can tell you, you'll get a true power factor of 0.99. And I will talk a little bit about the total harmonic distortion 5% and what's the significance of it a bit later on. But this is the practical formula that practical engineers use when they calculate the true power factor for a nonlinear load or a combination of nonlinear loads. Just talking a little bit more about the harmonic current and the problems that happen due to the harmonic current. Basically, it results in the heating of appliances or applications or loads. So higher frequency currents, they add together and can overload the neutral phase. The higher order currents also add obviously to thermal losses in the copper conductors and laminations of transformers and induction motors. They also distort the voltage waveform, which means that if there are other loads in parallel sharing the same bus, then it will potentially affect other linear loads sharing the same bus system. And also it potentially can also interfere with the telephone system as well. So there are quite a few adverse effects of harmonic current. And this is the Cappuccino principle that I was talking about early in my session. So obviously, in a mug of coffee, there is an element of froth, and the way practical engineers look at the relationship between real power factor and reactive power factor and total power factor is the relationship between, how much in a cappuccino is real coffee component and how much is the froth. And you'd agree that for people who love cappuccino, and I'm a great fan of cappuccino, I love cappuccino, you really do not enjoy the full taste of the coffee without some level of froth in it. So, and what that means is that you cannot really eliminate completely reactive power. You can minimize it to as much as possible, but in theory, there will always be some level of reactive power as a component in the power factor. This leads to power factor correction. So some of you maybe in your second year or third year and beyond would have already been introduced to the concept of power factor correction. So power factor correction, we talk about displacement power factor for a sinusoidal situation, and typically those power factor correction is achieved by using typically shunt capacitors. It's pretty simple. You put a bank of capacitors and that brings down the reactive power. Say, for example, in this example that is shown from 75 kVAR to 20 kVAR, and the total power or the apparent power also reduces significantly for the same real power. So the real power is the same. So for 100 kilowatt of real power, you are using much less apparent power, because we have been able to minimize the reactive power, which is pretty much contributing to the loss in any system. When we're looking at true power factor in a non-sinusoidal application, the common techniques for power factor correction is passive power factor correction, active power factor correction, hybrid PFC, and isolation transformers. Mostly it is passive PFC and active PFC. The hybrid PFC is nothing but a combination. It is an engineering compromise between passive PFC and active PFC. What is passive PFC? Passive PFC is basically the simplest way to control harmonic current by using a filter. So it is a very simple filter. It can be a big inductor or a choke, or it can be a choke with a capacitor. So what it does, it filters the higher order harmonics and only allows current at 50 or 60 hertz to flow through, which makes the non-linear load behave and look like a linear load. The more advanced technology, a little bit more expensive, but with much better outcomes and result, is what is known as in the engineering world as active power factor correction. So active power factor correction is a more complex electronic circuit. Some of you may have or will come across at some point of time in your power electronic studies concepts of boost converter, buck converter, buck boost converter. So these are typical electronic circuits that are employed to achieve active power factor control systems. And what this does, this is an electronic circuit. What it does, it actually controls the current that it is going to draw from the source. So it only draws as you can see, the active power factor control, the current controls the input current. So that's the fundamental difference. It controls the input current of the load so that the current waveform is proportional to the mains waveform, thereby getting to a situation where the power factor can be as close to unity. And this is a concept. This is a technology that is employed, but there are different variations to this active power factor correction. It can vary from product to product. It can vary from manufacturer to manufacturer. So some manufacturer A they will still do active power factor, but they may have a completely different circuit, which will be their intellectual property, their design. Manufacturer B will still employ active power factor correction in theory, but they may have a very different design, which is again their intellectual property. So, but in principle, they would be using something known as what we call in basic engineering, electrical engineering, active power factor correction. What are the benefits of power factor correction? Of course, one of the immediate benefits is in electricity tariff savings, because we are able to significantly reduce the reactive power component. And as a result of which, the network service providers, you probably come across, it is also very common in India these days, that the energy utility companies, they actually charge a consumer or a residential consumer for low power factor. So they will put a penalty that your building cannot have power factor less than 0.9. So as a building owner, I am responsible for choosing and installing equipments, the sum effect of which the power factor should not be less than 0.9. If it is less than 0.9, then I am liable for a penalty. So I have got to pay extra money to the utility company in compensation for the fact that I have not selected the right products, right components, which is resulting into a lower power factor. Obviously, again, with reduced losses, reduced, reactive power means reduced losses. It will obviously, again, reduce power drawn from the distribution system. So possibly positive effects, we can use lower size cables, because, a large part of the, one of the reasons why cables are oversized is to compensate for the losses. And if the losses are minimized in the first place, then the cable selection can also be more optimum. And obviously it results into stabilization of site voltage levels by reducing the inductive effect of the connective load. Getting into the efficient use of electricity at a very component design level. So I'm going to introduce to you 3 levels of use of electricity. One is at a bare component level, and I call an electric motor at a component level. So a motor with an integrated speed control, you see that big terminal box on top of the motor, that has got all the power electronic, the variable speed element integrated within the motor. So this is one of the simplest form of a variable speed controlled motor here, where the variable speed drive element is integrated into the motor. So, and why I say this a component, I will explain in the subsequent slide. But in terms of efficient use of electricity, we need to look at how electricity is being used at a component design level, how it is used at a product level. When I say product level, I mean this is an air handling unit. Air handling unit basically manages air conditioning of large buildings, theaters, hospitals. So this is a big product on its own. As you can see, this air handling unit has several components. One of the component is a fan. As you can see where, if you can see where the number 3 is written, that is a fan. Here, number 3, that is also a fan. And that fan is driven by an electric motor. So that fan, these 2 fans are components amongst many other components which make up this product. And this product is an air handling unit. And why I show this, because we may have different products, different electronic products involved within a bigger product, different electronic components. So I could have 2 fans being driven by 2 electric motors, and those motors will have speed control. So those speed controllers could be different. So it is one thing to look at for 1 fan, 1 motor, 1 speed controller. But if you look at it from a product point of view, which is this air handling unit, it has got a couple of different fans, few different motors, different variable speed drives. So the combination of this will have a very different impact on the power factor. And as I highlighted here, there is a very old engineering saying that the sum of the parts do not make a whole, which means that if I've got a product A, which has got, say, 1 electric motor, which is with a variable speed drive, which has got, a power factor, say 0.95, and I've got another one which is at 0.9, it does not mean that when I put the 2 equipments together in a product, the final product will actually have a power factor better than 0.9. It may actually have something less than 0.9. So there is a responsibility at the product level designing to have a power factor which is still meeting the standards of a building or whatever the application is or whatever the consultant is talking in a standard. And then we go to the next level, which is the system level. So I just showed you an air handling unit. These are typical buildings. So one side you have the residential apartments, and the other side you've got commercial buildings. Here again, in a building, you could have many, many electrical devices. You could have a pump. You could have different fans. You could have different application loads. Some of them will be linear. Some of them will be non-linear. And each of them at the component design level will have their own power factor. But when they all combine together, they all, the combined overall effect, this, if I look at this commercial building, for example, it draws power from the utility at one particular point. And that point is known as point of common coupling, which feeds power, typically, obviously, three-phase power to the building. So the owner of the building has got a responsibility towards the electricity supplier that he will maintain at that point of common coupling a minimum power factor level. Sometimes they may talk of power factor level. Sometimes they may even talk of total harmonic distortion level. So they might say, we want you to maintain a power factor level of 0.99, or they might say, we want you to maintain a total harmonic distortion level of no more than 5% at the point of. And that reference point can change within the building. So it is dependent upon how that point of common coupling is defined by the electricity utility company and what is the agreement between them and the building owner. But the building owner, and at a grassroots level, at the residential apartment, every tenant or every owner of a flat or a unit is also an owner, and we've got a responsibility. I've got a responsibility for my flat where I live here to make sure that I use electricity that I'm taking from the utility company in a responsible manner. This is just, probably this shows, what is at my home. So I pay electricity bill to AGL, the Australian Gas and Light Company. And my electricity bill depends on a number of factors. It depends on my daily usage, using power during peak and off-peak usage. It depends also on how efficient are my appliances at home. What's the quality of the fridge that I use? What is the quality of the microwave oven that I use? What's the quality of the dishwasher that I use? What's the quality of the LCD TV that I use? What's the quality of the computers and other devices, the printers that I use? All of that contribute, and they all have an impact on the money that I pay to the electricity company at the end of the month. And because all of them have the cumulated power factor effect. So if I am not being a responsible tenant or an owner, and if I do not think whether I am using the right gadgets and the appliances, I will end up paying high dollar at the end of the month to my electricity supply company. Not because I'm using electricity too much, but I'm also using electricity inefficiently. Just at a very commercial level, I'm just going to quickly talk about a green star rating. There are similar sort of concepts in India as well. Let me see if I can quickly get into this this link, and I'll probably not be too far away. So this should open up a web page that talks about the Green Building Council in Australia. So this is an initiative. This is typically what happens in any developed country. So this is a local initiative. Every building, every commercial building can actually apply for a particular green star rating. And the green star rating relates to how well that building is managing its resources. When I say resource, means water and electricity. So it takes into account, how efficiently and how responsibly that particular building is handling water as a resource and electricity as a resource. And there are star ratings from star rating 1 to 6. As you can see, up to 3 is bare minimum. Nobody even talks about that. It's only when it goes to star rating 4 and above that that particular building gets a certificate, and it shows a star rating 4 or 5 or 6. So I just wanted to give you an example of a practical real life in the world, how buildings are classified for their performance. And one of the key performance areas for a building is how efficiently they manage their power factor as well. So that was a quick thing about the efficiency of a building. Just one slide on some of the common test and measuring instruments. Some of these some of you who are students may have already come across. If not, you will come across, or at least if not now, when you start working as a practical engineer, and if you get involved in understanding harmonics. These are typical equipments that we come across in the market, in the industry. So one could be as simple as a handheld digital harmonic analyzer. One could be on the right-hand side, as it shows, is a little bit more complex. It has got more functions, and it could be, these are still portable. So sometimes, you never know, as a practical engineer, you may be employed as a site audit manager. You may have to go about in a site doing audit of a big steel plant, for example, or power plant, or any industry, any manufacturing premises, or an automotive manufacturing plant, for example. You may be wanting to carry out an energy audit, and one of the fundamentals for energy audit is to do is to scope and understand how efficiently that particular factory or that manufacturing company or that plant is using power. So understanding the harmonic levels at different equipments, and this test and measuring equipment that is used in the practice, very, very useful. There is, I think I found this on one of the links. These are very complex technical products. You never know, some of you may actually get involved in actually designing this sort of equipment. So I wanted to introduce to you, as you can see here, these sort of instruments, you can measure harmonics up to the 50th harmonic level. Yeah, and it can give you power factor levels. It can give you total harmonic distortion. Very, very. See here, total harmonic distortion, voltage, total harmonic distortion, current. As low as less than 3%, as low as less than 1%, you can still measure. So this is a very practical, user-friendly test and measuring instrument, something which practical engineers will come across quite often in a day-to-day scenario. Then just moving on, a couple of standards related to, which have relevance to harmonics and power factor correction and mitigation. One of the more common ones is IEEE, the Institution of Electrical and Electronics Engineers. IEEE 519 talks about harmonic mitigation. IEEE 1159, it talks about recommended practice for monitoring electric power quality. We have got then several IEC standards, International Electrotechnical Commission. You'll be exposed to these sort of standards as a practical engineer. You cannot remain away from knowing standards. As a practical engineer, doesn't matter which line you are in design, R&D, in sales or application engineering, product development, you will always be exposed to standards. So, and this is also reference to a local Australian standard where it talks about disturbances in main supply networks. So this is just a very sneak peek. There are many other relevant standards on the subject of power factor and harmonic. This is a very wide topic within electrical engineering. I could typically be talking for many more hours on this particular topic, but I thought that I'll probably just introduce all of you to this topic, because power factor and harmonics are not my creation. They are good old electrical engineering theories. Okay, power factor as a concept, it goes back to centuries ago. Okay, harmonics is also not new. But why I brought up this topic and why this topic I thought I will introduce in this forum is because new. But the application of power factor, application and the implication of harmonic distortion and what it means in different contexts, in products, in components, at a system level, that is what is important, because there is growing awareness within the industry, within the society, within the community, at system level, at product level, at component level, of the importance of power factor and harmonics and harmonic distortion. That is so far as I'm concerned for now. So I'm throwing this forum open to anyone who wants to talk to me, put up some questions. I will try and answer as best as I possibly can. And where I cannot, then I will definitely take notes, and I'll probably request the moderator to make some notes and email me the questions, and I can take it up from there. So thank you very much for listening to me and listening to me with patience and not interrupting to me. I truly appreciate that. And now over to all of you.
Thank you, sir. Thank you for this wonderful